Okay, here we go. Recording ICS 12. So a triple nested integral that represents mass. So the density is the integrand. So let's pause on that. That's the easy part of the problem. So the region that's defined by, wow, there's a bunch of little stuff in here. So we're looking sort of, the first inequality says we're looking inside the unit sphere. The second inequality, wait a minute, what is this? Z equals square root of x squared plus y squared. So z equals r, right? So let's see, z equals r. In cylindrical coordinates, that makes sense, but what is z equals r in spherical coordinates? Claim it's a cone, by the way. Does that make sense? Z equals r? Maybe I better draw this picture. Let's look at this equation. And I know that we were given a greater than in the problem, but let's look at z equals square root of x squared plus y squared. Well, I'll tell you what, chapter 2 techniques, you can view this as a rotation. And I claim it's a rotation of a line with slope 1 rotated around the z-axis, and that makes a cone. Does that make sense? Yeah, okay. So, okay, so let's start drawing our picture. We want to look at the region that's inside the unit sphere. Then let's see, the second inequality, it says, we don't need that anymore, above that cone. And it's a cone of angle 45 degrees. So we've got, this is going to be a little hard to draw it. We've got a cone sticking up here. So inside the sphere, above the cone, so we've got, you can start to see our little guy here, right? It's a little kind of ice cream cone thing down there. And I want y bigger than x. Okay, let's see. So y bigger than x. Okay, so y, here's y, and here's x. So that means I'm going to look at this plane. That's the plane where y equals x. And I want y to be bigger than x. That means I want the part of this that's on that side of the plane. Is that cool? Now, our picture is way too busy at this point. But we see the three things that we're dealing with. So let's redraw our picture, and let's just try to draw we've got this ice cream cone that's sort of, again, inside the cone, inside the sphere, but I want to draw, it's been kind of sort of sliced in half by this plane, and I want just the part on that side of it. So this is going to be a little hard to draw, and I'm going to do a bad job of it here. I'm pretty sure. But again, all it needs to really be is sort of qualitatively good enough. So I've got this, here's kind of a little guideline in the XY plane. And it kind of, let's see here, it kind of sticks out like that a little bit. So it's like an ice cream, sort of like an ice cream cone, kind of, but it's been, but it's been sort of cut in half tall ways at that angle. It's hard to see, right? Now this is a bad picture, but I think that between the two of these, we're going to be able to make sense out of what we really need out of this. And in particular, I just need the bounds on the different spherical coordinates. And let's start writing stuff down. So we know we've got rho squared sine phi d rho d phi d theta. This is always that order for spherical coordinates. So step one, what's the range of values of theta? Well, gosh, this thing sure is ugly, but it's theta-wise, it's not that bad. Theta-wise, I just want the stuff that's on that side of this sort of guideline that I've drawn here. And this is where theta is equal to pi over 4. And this value of theta over here, sort of theta 2, that's just 5 pi over 4. Does that make sense? So pi over 4, 5 pi over 4. Okay. All right, next question. What's the range of values of phi? Well, theta kind of doesn't matter anymore. I'm now going to be looking at planes hinged off of the z-axis, going to fix a value of theta. And so the fact that I've taken a slice off on that side, I don't really care about that anymore, right? I'm just looking at sort of inside of this plane here. And inside of this plane, we can draw the two different other pieces. The two different other pieces are, well, we have the sphere, and the sphere is easy to draw. Inside of that cross section, it's just going to have a cross section, it's just going to be a circle. The cone in this plane is just a line. Well, let's see here. Yeah, so the cone is just, I'm going to draw a line like this. And so this is the part. Now my picture is pretty bad at this point, but in fact this picture is sufficiently bad. Let me draw a new, let me try to replace this with a new picture now. And I want to draw now just this theta plane. Okay, so just the theta plane. So for that, for some particular value of theta, there's what the sphere looks like in that theta plane. Here's what the cone looks like in that theta plane. And I want the part that's above the cone and inside the sphere, so this is what we're talking about here. All right, see, that's the z-axis. This is a particular theta cross-section. So what can I say about phi? The range of values for phi, well, phi 1 is 0, and phi 2, well, that angle, well, we've agreed that angle there is 45 degrees, right? So that's pi over 4. Does that make sense? Yeah. Everybody good with this? Okay, so 0 to pi over 4. So, notice we've drawn a lot of pictures here. When we drew the original three things, picture's too busy. It's kind of hard to make sense out of, but you can kind of get a geometric intuition, maybe sort of draw a, look how bad that picture is. That's terrible, right? But I mean, it's good enough to at least kind of get started and see the range of values of theta in this integral. Then we had to really come and see now a different picture where we didn't really use this at all. We got this picture by thinking about what's going on here. I'm looking at a particular value of theta, some particular cross section over here in some direction, and in that theta cross section, I just say, well, what does the cone look like in that theta plane? Oh, well, it's a line. The cones are great inside of a cross section of a plane. Sphere becomes just it's a bit of a circle. Then it extends down here, but it's not really relevant for the problem. Okay, and then the last question, what's the range of values now for rho? Well, so I've got to pick a value of phi. And on that value of phi, whoops. Oh, there's pins. Not happy. So there's the smallest value of r. There's the largest value of r. Conveniently, that's r equals 0. I said, rho, excuse me, that's rho equals 0, right? And this is where rho, well, what do we know about rho there? Well, that point is on this curve. This curve is a cross-section of the sphere, which, of course, has rho equal 1. So rho goes from 0 to 1. Everybody good? So we've got that bound stuff all figured out, and now the rest of the problem is no big deal. Let's see, representing the mass. So the integrand should be the density. So in here we put density. Density is y squared, but this is in spherical coordinates. So y squared, let's see, what was y? Y is rho sine phi sine theta. So there's rho, so there's y squared. So this is your density, y squared. And then you can multiply this out a little bit. I mean, you're going to have rho squared there, but you have a rho squared there. So you have rho to the 4th, and then you have sine phi squared times another sine phi. So you get sine phi cubed and then sine squared theta. Yeah, lots of pictures. Don't be shy with pictures yet. And here's another thing. I kind of wish I'd remembered to say this in class. When you're drawing a picture, don't draw too small of a picture. Honestly, that's really smaller than I should have. Go ahead and draw yourself a nice big picture, because notice how very often you find yourself kind of cramped. And I see students do the following very often. I see students trying to draw a picture about this big for the whole thing. And they're like, okay, it's all right. Now here's my picture. There's the sphere, and there's the cone, and then we have this plane cutting through there like that, and they're trying to make sense out of stuff with that little picture. Come on, that's why. It's too hard, right? Draw yourself a nice big picture, and really several of them, right? So we used all three of these pictures in the solution of this problem. Yeah. Right. Okay, any other questions on this problem? Pretty good? Yeah, right. So the reason rho is from 0 to 1, because, so if you look at, so on this picture, there's the last value of rho. When we picked a theta cross section, we now picked a phi cross section of that theta cross section. We have this. Sorry. We have this. That's my range of values for rho, and that point that represents the largest value of rho, that point is on this curve. And what do I know about that curve? Well, that curve was the cross section that I got of the sphere inside of that plane. So the point is, this point that represents the largest value of rho, that point is ultimately on the sphere, and the equation for the sphere in spherical coordinates is rho equals 1. So I need to solve for rho in that equation, which has been done. Yeah. Yep, sure. Okay. All right.